All right, everyone. Good morning. Let's get this recording going. All right. Did you have a good break? Yes? Did you sleep? Get some good sleep. Maybe go somewhere fun. Maybe do a little bit of work. We'll see. All right, just a few reminders at the beginning, if you would please listen. You do have that pre-lab 5 for this week, and you have until Friday to address your questions. I usually arrive to class a little early, and I can always stay if we get done a little early afterwards, so ask your questions then or in office hours. But you have to do that by the end of the week for your exam 1. Exam 2 is at the end of March, the last day of March, March 31st, that Thursday night. So we'll tell you more about where the material will end and so on, but we've got a few weeks left. Homework 5, as I mentioned before, homeworks are going to be turned in on Thursday at 5 o'clock from here on out. Gives you 1 extra day past a Wednesday lab if you have a lab on Wednesday, in case they revisit an idea from that homework and you want to double check something. And if you're ready to start, I will be glad to give you a good hint on homework 5, problem 2. Do you have any questions or comments before we do that? How many of you started homework 5? Started, that means maybe even looked at it, hopefully. Homework 5. Take a little note if you'd like, or just listen. There are 9 questions on homework 5. There are 2 that require a picture you sketch and you upload. I want to talk a little bit about questions 1 and questions 2, but I need you to be ready to listen. So I'm going to just read the background for question 1, and it's very small print. All right, this is about selecting samples of 190 students and asking them how many hours of sleep did you get. Suppose in the population of all students, the mean amount of sleep is 7.05 hours. It even says here for question number 1, suppose in the population, the mean number of hours of sleep, mu, equals 7.05. It gives you the mean for the population, the parameter. And then it says the standard deviation, and tells you that sigma is what? 1.75 hours. So it gives you the mean and standard deviation for your population of values. And then it starts to talk about what if you considered taking samples of 190 students over and over. Part A, what is the value of the mean of the sampling distribution for the possible sample means? Boy, that's a long sentence, isn't it? What if you were to take samples of 190 and consider calculating the sample mean x bar? A, B, and C are having you work with and tell me about what you know about x bar in terms of what its values might be. What are the possible values for x bar? What's the mean for those possible values of x bar? Now we had 2 results that told us about x bar and its model. We called one of them an exact result. The exact result required that the original model for your population of how much hours of sleep you get, you should know is normal, with some true mean, some true standard deviation, and then no matter what sample size you take, x bar will be normal also for its model. That was the exact result. But do we have that here? Did it say in the description that the model for amount of time that you sleep is normally distributed? Nothing about normal given. So what saves us here? Our sample size is 190. So by the CLT, what do we know about x bar? We know it's going to be approximately normal because the sample size is large. X bar will be, here's the exact statement from your yellow card, approximately normal. And it tells us that the model is still centered at mu. The X bar values, the possible sample mean values, have as their mean mu. You would expect X bar to be the true mean mu on average. And then what was that new standard deviation for how averages for a sample tend to vary around that true mean? It was not just sigma anymore, because that was for individual values, but sigma over square root of n. Because averages based on a random sample should not vary from that true mean mu as much as an individual value could. Individual amount of sleep can vary, give or take almost 2 hours, 1.75. But if you were to take 190 measurements and average them, you would hope that that X bar would be pretty close to the true mean mu. And how close would you expect it to be to that true mean mu? Well, here's that average distance idea. So are you able to work out that normal model for me? Could you actually draw it if you are asked to? You have mu and you have sigma. So you'll be able to talk about what the true mean is for your X bar values. That's what question A is asking. What is the expected value or the mean for all the possible X bar values? Where do the X bar values center at? What is their mean? It is mu. And mu is 7.05. And can you work out the standard deviation? And if you have a normal curve, what's that really nice, simple rule that we learned back in Chapter 2 that applies for normal curves or bell curves? It's called the empirical rule. You know that if you went out one standard deviation, what percent of the values, if they're normally distributed, should be inside within one standard deviation? About 68%. And if you went out 2 standard deviations, about 95%. And you use that to work out part C, because you have the mean and you have the standard deviation. So question 1 gave you directly, you have a population, you know the true mean, let's suppose it's 7.05, you know the true standard deviation. Now let's think about what could happen if we take a large sample and calculate X bar. What are the possible values? What's going to be the mean of those possible values? What's going to be the standard deviation? And then can you come up with a range where you think 95% of the values will fall? All right, now that's a little different with question number 2. Question number 2 starts out with the phrase, let X is a random variable, let X be the salary in thousands of dollars for a randomly selected full-time worker. Suppose the mean, or it puts in parentheses, or the expected salary, suppose the mean or expected salary is 62, and this is in thousands of dollars, so that's 62,000 of dollars. And it tells you that the standard deviation for your variable here is 12. That's all you have as the background. Let X be this random variable. So can you imagine a population and X is your variable? And you're told, suppose you know that the mean or expected salary is $62,000 and the standard deviation is 12. So I need a symbol to represent that 62 and that 12. What's the appropriate symbol? If it's a mean or expected value, then what should I use there? Mu. It's not said anything yet about taking a sample. It didn't say that this is the mean and standard deviation based on a sample coming from your population. It says let X be the variable, the random variable, and when you talk about the mean or the standard deviation for a random variable, Chapter 8, we're talking about mu and sigma. So the notation here, not implicitly in the question, but this is mu, and this is sigma. Now again, question A starts out with, well, what if you were to take a sample of 64 salaries? So N is 64 here now, not 190, but it's still decently large enough, right? And it asks you, what do you know about the model? The distribution for the resulting X bars. Well, can't we just use what we wrote up above? Won't this thing work again? If you take a random sample of a decently large sample size, X bar will be approximately normal. So can you again draw me a picture of that model? I'm asking in question 2 for you to draw the picture. You don't have to draw it in question 1. You just have to state the mean and the standard deviation and use it. But you do have to draw the picture for the values of x bar that you could expect to get for part A. Part A is an upload, draw me that picture, this model that x bar will follow approximately. And then in part B, it asks you to find a probability. Find a probability that the sample mean you might get, what does it say, exceeds 65. $65,000. Now, as soon as you start thinking about x bar and mu, most of the time we start thinking about t's. But that is correct if you're doing a hypothesis test. If you're doing an H0 and HA, where you only have your sample, you have a hypothesized mean, but you don't have sigma known, then yes, you are going to have to do a hypothesis test with a t statistic. But there's nothing about hypothesizing here. We are told the mean is 62 and the standard deviation is 12 for individuals. We can draw that model for x bar, and all I'm asking you to do is find a probability under that model. So if you can draw a normal curve and you do know the true mean and you know the true standard deviation, can't you find 65 out here and find the area under that curve? How would you do that? What kind of quantity will you have to calculate as a first step? A z. And it's not a test statistic, it's a z statistic because it's calculated from the sample, but it's not a test statistic value for some hypothesis test. It's a z score because you do have the mean and standard deviation to subtract and divide by. You're not doing a hypothesis test here. You're just working out, and reference for this question, the ACT score example we did on, I think it's on page 109 of our notes, is a good reference for that question. I get a lot of students trying to go and mix up. They draw a normal curve, but then they go to t's. And it's true, when we're doing hypothesis testing, there's a normal model assumed for your population, but you don't know mu. You hypothesize mu. You don't know sigma. You only have a sample. And that's where you get stuck then. I can't calculate that z because I don't have the sigma over square root of n on the bottom. I only have s over square root of n. So after you get through questions 1, 2, and 3, which is about chapter 9, which is not doing hypothesis testing yet or confidence intervals, then you move on to questions 4 and question 7. And I just want you to listen to the difference of what you've got in those questions. Question number 4 is, suppose you take a random sample of 18 U of M students. You measure how much cash they have in their pocket. The resulting mean is $18.25, $18.25. Okay, stop right there. You took a random sample of 18 people, and the mean turned out to be $18.25. What would be the symbol for $18.25? X bar, not mu, because it's based on the sample. And you have, after that same sentence, and a standard deviation is 3.55, $3.55. What's the symbol for that $3.55? Because it came from your random sample. S. Right, that's all you have. And then it asks you, we would like to learn or estimate the true mean with a 95% confidence interval. So you're going to have to make your confidence interval, and when you're doing inference of a confidence interval or a hypothesis test, you are using t's. You're going to have to look up a t star, or if you're doing a hypothesis test about what that true mean might be, you're going to have to calculate a t statistic. Okay? Question number 7 is a hypothesis test. Question number 7, background. It gives you the H0 and HA, so you know you're doing a hypothesis test about the true mean mu. It's a mean breaking strength, average breaking strength. And it says a random sample of 41 hinges gave a mean of 162. If a random sample gave you this mean of 162, what's the symbol for 162? X bar. And same sentence, and the standard deviation is, the symbol for that will be S. And it's asking you to do the test. The first step is to compute the value of the test statistic. Well, when you have your sample mean and you want to subtract the true mean, you can't do that because you don't know the true mean, but under H0 you know the true mean. So that's the first step that you get to do still. It looks like a z-score starting. But when you divide, you can't put down there sigma over square root of n because you didn't have sigma anywhere. hypothesized or known. You only have S. So now you're doing a t-test. And the distribution of any t-statistic is what kind of distribution? What kind of model do you draw for the picture of your p-value there? It's going to be a t-distribution. Label it with a t with a certain degrees of freedom. You have to draw that picture for question 7. Part B says draw the picture of your p-value. Well, if you calculated a t-statistic, it's going to be a t-distribution and give all the details. But note the difference between question 2 and then question 7. Question 7, you only have data and a hypothesized mean because you're doing a test. Question number 2, you're told the variable, here's the true mean, here's the true standard deviation. You have the model with the true mean and standard deviation. So when you find probabilities about x bar there, yes, you start out x bar minus mu, but you're able to put sigma over square root of n on the bottom. So it's a z. All right, because a lot of questions have started to come in on that, and that's a very common place of confusion. So I hope that helps. That's your homework 5. It's all about the parameter mu, either estimating it, learning how x bar does at estimating it, or testing hypotheses. Those are 3 parameters now. What are they that we've done? We have done a population proportion P. We have done all of that. In fact, that was on exam 1. That will be on exam 2. Exam 2 will be about the 5 parameters, about how to test them and hypothesize about them or make a confidence interval for them from chapters 9 through 13. So that's the focus of exam 2. We have covered proportion P. We have covered P1. It's not on your page 131. Minus P2. This is your yellow card. And we have now covered quite a bit of this third column about mu. There are 2 more scenarios left. They happen to be ones in which you have 2 sets of data, like we did with 2 proportions, but they're on the means side when we're doing quantitative measurements. Today we're going to go into the paired design, where you have 2 sets of measurements, but they match or pair or go together, where each person can be their own control. Here's where I was before, some treatment, here's my after measurement. I'm my own control to see if there was an effect of that treatment. We want to build in control. And if we only have 1 sample and we give everybody the treatment and measure how many days to cure, that's going to be subject to that placebo effect and other biases. So we want to have ways of analyzing data where we can have a control group, and that's where we're going. All right, page number 135 of our notes. The paired data scenario, which is what your homework 6 will be talking about. Working on that right now. Chapters 9 through 13 focus on sampling distributions, confidence intervals, and hypothesis testing. And you go through that same 3 cycle of those things for each of the different scenarios. There's 5 of them. So when we get to practicing for exam 2, most likely the hardest part will be making sure you can identify for that problem what scenario you're in. Is this the one about mu or mu d? Or p versus mu? And that's just reading the question, measuring, figuring out what you're measuring. Do I have 1 set of data or 2? So we'll go through that practice. Pair data is identified when you have 2 sets of measurements, but they're matched or paired and go together. The classic pair design is before and after, or 2 measurements on the same person or part. Then you know they have to go together. If you measure a before and an after on the same person, why would you compare those 2 numbers? Because they came from the same person. And they might have had a low blood pressure to begin with compared to the others, but now is it even reduced more compared to where they started? So when you measure the same characteristic twice, maybe under 2 different conditions, or that classic before and after, give a way of paired. But there are other ways to have paired measurements. I could have 100 subjects for my study about which teaching method is better. And what I might do is match or pair up those subjects by a pre-test result of where their basic level of understanding is, so they are alike. And then randomly divide one into one group or one into the other group, but they're matched or paired to compare an alike person with alike. I match or pair by age, previous heart condition, so that these 2 treatments can be compared for 2 people that are very similar with other possible confounding variables. So that's another possibility, is you actually do pair up your subjects So they are two separate people, but they're meant to be put together because they have common characteristics. All right. The parameter in this case, though, is not two separate sets of data where you analyze the two means separately, but rather you're focusing on the differences. In a pair design, I don't really care what their cholesterol measures were before or exactly what those values were after, but rather was there a decrease? Was there a change from person to person? I want to know about the difference. So we're going to focus on the differences. I'm going to think about having just one population of all the possible differences now. The differences in scores under the two different treatment methods they received, or the difference in blood pressure or cholesterol level. And so I'll take from that population one sample. Now, before we represented our sample with X's, now we're going to call them D's for differences. Before we talked about the mean of a population being mu, now we put that little d as a subscript because we're talking about differences. So we put this here to remind us that we're in the paired data scenario. So if I'm trying to learn about and have a population of all the differences, and the quantity I want to learn about for this population is the true mean difference. And I can't look at everybody, so I take out a random sample, and I get those differences that I observed. What would you do with that sample? Same problem as what we've been discussing in your homework 5s about. You want to learn about the true mean. You've got a sample. You're going to calculate the sample mean. What will we represent the sample mean with here? Used to be X bar. Now we're going to call it D bar, the average of the differences in our sample. The sample differences and their average should hopefully help me to understand what the true mean difference in our population might be. So it really is our one sample problem we've been doing before. We're going to talk about t-tests and t-intervals and so on. But now it's on differences, so we just have a little different notation to remind us. We've got control in our study. We've got paired data. Got a couple examples that are here. These are from Chapter 9, where they're introducing each of the 5 scenarios. This is number 4. One of the research questions could be, what's the mean difference in weights for freshmen at the beginning versus the end of their first semester at school? What's the mean difference in ages between the husband and wives for a certain area? The parameter and the statistic. So in our yellow card, this information falls under the same column for a single mean mu because it really is under that same idea. It's just on the differences. So let's take a look at the background that is regarding that first research question. It comes from your text. A study to learn about the average weight gain or weight difference for first-year college students. We have a sample of 60 students, and their average weight gain was 4.2 pounds for that first 12 weeks. So what they did is they measured a difference in weight. They took the after the 12 weeks minus the before. So there is really going to be a gain if it's positive. If the average weight gain was a negative, it would have been that they lost weight on average. Okay, but you have to define your differences. That's one of the keys. You actually have to be careful on how are you going to define the difference. After minus before or before minus after? Because that'll tell you what kind of numbers you're going to look for. Can we identify the population versus the sample? Who are we trying to learn about? Population is all what? All first-year college students. And whatever their weight differences are, their weight gains. The sample that we selected from that population consists of the 60 students that were randomly selected. And whatever their measurements are, that sample would be represented by D1, D2, their measurements up to D60. The parameter versus the statistic. Parameter is the true value for the population. I'm trying to learn about the true mean weight gain or mean difference. Mu sub D is our new parameter. It is the population mean weight gain, and this would be for all first-year college students. I'm sort of being redundant here, but I'm putting in that it's a population mean and clarifying what population it is the mean of. The mean weight gain for all first-year college students, or the mean difference. Difference defined in this way. And of course, our statistic is not mu d. We don't have that quantity. We have what we call d bar. This would be the sample mean. The sample mean weight gain for the 60 students that were selected that make up our sample. Now, mu d. Does anyone know what mu d is? Can you tell me its value? Is mu d 4.2? 4.2 is what here? D bar. It's the mean of the sample that I got. D bar is 4.2. Mu d is the parameter. Does mu d vary? Does it have a sampling distribution? Mu d is a fixed but unknown quantity, fixed but unknown value. Parameters don't have a distribution. They are a number that I'd like to learn what it is or estimate it. So mu d here is fixed, but it's unknown. And I'm trying to estimate it or test maybe a theory about it. It is d bar here that we do know for our sample, don't we? D bar equals 4.2 for our one sample that we selected. 4.2 pounds. Well, you've got those couple of classic questions that come every time we introduce a new statistic to estimate a new parameter. Is there anyone who can tell me how close is 4.2 to that true value mu d? I mean, how accurate was this 4.2? How far away am I? How close is our sample mean difference to the true population mean? We can't say that, right? Because mu d is unknown. You can never say to your boss, here's how accurate my number is that I just got for you for my sample. I can't tell you how accurate that number is. I can tell you how accurate the process is that I use to give you that number, but not that actual number. Can we say how close? No. That's because mu d here is again unknown. We know this margin of error idea or standard error idea helps us to quantify how close such values would tend to be to the truth. That's the process part, but not any particular value. What if we took another random sample? Are we going to get 4.2, 4.2 every time we take 60 students and get their average weight gain? No, probably not. It's going to vary some. It might get another 4.2 somewhere. It will possibly have some numbers that repeat, but they are going to vary. What are those possible values if we did take many samples over and over? What would the distribution of those possible sample mean differences be? In other words, what is the sampling distribution of this new statistic? But it's not really a new statistic, is it? Isn't d bar just x bar in disguise? So don't we already know our answers? We went over the two answers in the beginning of today. We had an exact result and we had an approximate result. Approximate result is that nice little safety net called the CLT. Or we could maybe use the exact result, and here they are. If you have the true mean difference for the population and the standard deviation, and then you take some sample that's random, if you know that your differences have a normal distribution to begin with, the differences in weights, if you sketch them and looked at the model, would be normally distributed. The differences in scores, the differences in cholesterol levels, whatever it is, if that response has a normal model, then you can take any size, large or small, but make sure it's a random sample, and calculate that d bar, and we know what resulting model we'll get for the values that the sample mean difference could be. It will be normal, centered around what? It's an unbiased estimator, so it's centered around that true mean of the differences. You'd expect that true value. But now that standard deviation for averages, averages vary less. How much less? Well, you get to divide by the square root of your n. Your n here is your number of differences in your sample, your number of pairs. In the weight gain problem, there were 60 befores and 60 afters. There were 120 measurements made, but there were 60 differences. So 60 would have been our n. This is the exact result. It works no matter what sample size we have. This is why in your t-tests, if you have to list the conditions to do a test, we say you have to have a random sample. Sample needs to be a random sample, and your population needs to be what? Normally distributed, so that we don't have to rely on having a large sample size to do the test. That's why that condition of normality for your population is stated. So we could use this result. But then the safety net comes in and says, but if your population is not normally distributed, skewed drastically or outliers, but you take a large enough random sample, then the distribution of your sample mean, you can still use that result. It's just an approximation, but it works. It's not exactly, but it's approximately, and you get to write out the same model. In order to do your t-tests or your t-intervals, what we need is this model to hold approximately for your sample mean. And so we assume for doing those procedures that you have a random sample and you have a normal distribution for your population. That is relaxed by the second bullet here, because if their sample size is large, I don't have to worry about the normality in the original population. I will still get the normality I need for your sample mean. All right, this is the famous result, variation of it anyway, called the CLT. All right. A couple notes are on the next page. We're going to cross out the 30 and put in a 25, because we have mentioned we'll accept 25 or higher as being the large guideline. And that's mainly because the applet that is really nice for you to play around with that you did before break showed normal curves coming out. No matter what kind of original model you might have drawn or sketched in that activity, you could get normal models coming out for 25 observations. So that's sort of the arbitrary. It's arbitrary. If your model is only slightly skewed, it's possible you'd be okay with sample size of 20 or maybe 15 to overcome that little bit of skewness. If your model's drastically skewed, well, then the larger, the better. It is a limit theorem, so you get a better model closer to approximate normality than not if you have a larger sample size. So there's not one moment, and if I have 26, it's okay, and 24, it's not. It really depends on how non-normal your original population is. Now that standard deviation, you get to calculate something like that in your homework due this week. You get to do sigma over square root of n because you're told sigma in a couple problems. That does help me understand how accurate my process is. Gives me an idea of how far away d-bar values would tend to be from the true mean difference on average. But I usually can't calculate that. Sigma d is rarely known. So again, you fix that by putting in your S. The S that you can get on your data. You've got those 60 weight gains, weight differences. You can calculate the standard deviation of them and have your S. So you can still calculate this thing, which is not a standard deviation. It is a standard error. A standard error is an estimate of the standard deviation of that statistic. So it estimates that average distance idea. All right. With that, let's take a look at the background, and then we get to do one of each of these today. If we're going to do a confidence interval to try to estimate the population mean difference, well, then we'll use that same format. What do? We take our best guess, the sample mean difference. You usually go out plus or minus some margin of error, and that margin of error is composed of two main parts. There's this multiplier that we use, that few, and then there's this standard error because we can't put in the actual standard deviation. So the standard error has the S over square root of n, so n plays a role here. And one of your homework questions, don't you have to kind of list the different things that affect the width of your interval, right? And of course, the multiplier does. And so that's based on your confidence level that you want to use. What multiplier will we use here? If you're making confidence intervals, if it were proportions, you use a z star because you have a large sample size there. That's required to make that confidence interval for a proportion or two proportions. If it's a mean or a mean difference now, you're going to use a t star. And why do we use a t star? Because I don't require that you take a large sample size. So I might have to use the actual t-distribution model to find those cuts for 90% or 95% in the middle. So we'll use t-star values. And that means I have to use table A2. And table A2 has degrees of freedom to look up those multipliers. What's the classic degrees of freedom you have so far that you're using on that homework 5? If you have one set of data you use, and it's a sample size n, then it's n minus 1. The degrees of freedom for a pair design will also be n minus 1. The n, however, here is, again, the number of pairs in your sample, the number of differences in your sample. You might have 100 people, but you might make them form pairs being alike with some important characteristic, so you have 50 pairs. Even though there's 100 people being measured, degrees of freedom are going to be 50 minus 1, not 100 minus 1. All right, and then likewise on the testing side, you actually calculate some kind of standardized quantity. You take your sample statistic, d bar, just like x bar, and then you subtract off some kind of null value, hypothesized value, what you have in H naught. And then on the bottom, when we did proportions, we could put in a null standard error. Remember, it was p naught, 1 minus p naught over n in the bottom of that z statistic. You had the actual true quantity down there, but we don't have anything known about the standard deviation of H naught's true. So this is just the standard error. That will go down there. And so when I calculate that, and it's a standard error in the bottom, not a true standard deviation, even under H naught, then what kind of statistic have I just calculated? AT. And we'll be doing a t-test today, another t-test. The hypothesized value. Now on your homework, one of them was 160 for some measure of the strength, breaking strength, or some other value for the true mean. What will be the common value we'll use here for most cases? Because we're comparing before versus after. We want to know under H naught, there's no effect. The treatment is not effective. So befores and afters should balance out, and the average of those differences should be 0. So that's your null value. Now you could test for a certain type of increase or decrease, which can be done and adjusted, but 0 is the most common null hypothesized value. All right, there's my picture of the day. That's what I did the first weekend of break. Went skiing in Blue Mountain for a few days. My daughter had off the week before, and then we had off last week, so we did the common weekend and did a little something. And then I spent the rest of my break preparing for 2 talks that I had to give in Chicago about teaching, statistics, and a little shopping in there too. All right. Continue on learning about that population mean difference. Page 139. So we've already done the introduction, the parameter, the new parameter we're learning about, mu d. D is there whenever it's a pair design for the differences. We have some data. Sometimes the differences will be calculated for you and already defined as before minus after or whatever definition they use. Sometimes you'll have to calculate the differences. One of the homework problems on homework 6, there's just 5 observations, 5 pairs of mother-daughters, and you have to calculate the 5 differences, but they're easy numbers to work with. Of course, we'll take those differences and average them. There's our best guess at what we think the true mean might be, and its corresponding standard error to form our confidence interval. Same basic structure again for all confidence intervals. And so you've got your box. And I mentioned that every time you get a new confidence interval, that box is a nice box. It gives you the formula, which is on your yellow card, and it's there. It says paired confidence interval, that exact formula. Tells you the degrees of freedom to use. But what it doesn't say on your yellow card anywhere is the details about what's required in order to make that confidence interval. What are the conditions or the assumptions needed? There's still 2. When you're doing a test about a single mean, whether it's mu or mu d, or a confidence interval for mu or mu d, there are 2 conditions. One's about the sample, one's about the population. The sample needs to be a random sample. The population model, the model for that population, of quantitative responses needs to be normal. But look what's different here. It's all about the differences. So you have to be specific and say it's the differences that have to be considered a random sample from that population of all differences, and the model for the differences in scores, the differences in weight, needs to have a normal model. We can check those conditions, and we'll do that with our first example, but that sample size being large is not one of the conditions. So don't list that as a condition. I don't require you to do a t-test that you have a large sample size. It is nice when you have a large sample size so that if that second condition about the normal model doesn't look met, I can still go on and do it. My test or my confidence interval will still be valid because of that CLT. All right. How many of you have had piano lessons in your past? I have two. My daughter's taking them now. She always plays right when we're making dinner, so we have our dinner music. Looking at whether piano lessons help improve reasoning in preschool children. You've got some data on page 140. For 34 preschool children, where they took this test to measure this type of reasoning before and then after some period of having piano lessons. And what's already calculated for you here are the changes, the differences. So it'll be pretty important to know how those differences were calculated. Here it's after minus before. Larger values for either score and reasoning would be more reasoning capability. So if the piano lessons had some effect, then which one should be higher? The afters or the befores? After. After higher, befores lower, then we would hope we see a lot of positive numbers rather than negative ones. But we do see some negatives. We do see some positive. We see some zeros, right? There are some children for which there was no effect. There are some children for which their scores went down by 2 or 3 points. And there's some that even improved by as much as 9 points. So we have quantitative data. We're measuring scores on a reasoning test and actually calculating the difference in scores. That's a quantitative measurement. We have quantitative data. The difference is already calculated, so let's graph them. The graph you have provided for you is the histogram. We should look at our data first. If I graphed it and I had a bunch of data, I might see an outlier come out in the graph that I might not have seen in the long list of numbers. Maybe it's just a data entry error that I have to fix. All right, so there's our change in reasoning. Let's comment a few things here. First of all, the differences were after minus before. So we want to see, as we mentioned, positive differences in general. We're going to be estimating the size of the effect of piano lessons through a confidence interval, but we're hoping, of course, that maybe we'll establish that they were useful and positive differences in general. What was the average of those differences? It's reported right here, and you can kind of see that here's 0, so it is a positive number. The average of the differences was what? 3.6 reported here, and in the output right below it, though, it was what? 3.62. And that's D bar, right? That's not mu D. If you took the average of those 34 children and get 3.62, which is a little more detail in that second part of the output, that's not the average for the population of all such children. That's the average for my sample, so that's D bar. And it is at least what? It is not negative, but positive. Descriptively, we see some improvement. Descriptively improved. We haven't established whether it's significant or not, but it is showing some improvement, at least in the sample. How about normality then? We're told we have a random sample of preschool children. We could only infer the results to the preschool children like those observed. If they are the ages from 3 to 5, that's the age range. If they're only boys versus girls, and so on. But normality of the population of our differences, this is all I've got to look at. Now that's not a bell curve beautifully. But is there anything that's showing a strong departure from normality? Skewness or outliers? That's what you're looking for. It's a bit robust to departures from normality. It's not perfect. I only have 34 measurements showing here, but I'm looking for strong departures to say, ooh, maybe I'm going to have trouble with that normality condition. Although I do also have what? A sample size of 34, which is starting to be where we think is reasonably large enough to rely on that central limit theorem if we had to. So a couple comments. Our histogram here shows that the normality of the response, we'll even put here of the differences. Our response here is, is the differences. And it's reasonable. No strong departures from normality. No strong departures. There's no outliers that I would want to go look at and check out first. And also, we do have a sample size of 34, which could be in that category of being large. So it's safe to proceed and do our confidence interval. You might be asked to state the conditions. You might be asked to check the conditions. It's not easy for you to check the condition of a random sample without some detail of where the data came from, to know if that was reasonable selection and not selection bias and so on. But you will be able to perhaps have a graph or two to look at to check the normality condition. Here's a good question that students trip up on exam 2. I have data here on the reasoning scores, after and before. I could make two QQ plots for you. QQ plot of the after scores and a QQ plot of the before. But I'm not really looking at the normality of each of those. I'm looking at the normality of the differences. I would make one QQ plot of the differences here to show. All right, we've got some output. I mentioned that rarely on an exam do you have to calculate the sample mean or the sample standard deviation. Summary measures will often be provided, maybe through SPSS. So again, the notation for that mean. 3.62 is not mu d, but that is d bar, the mean of our sample. This is the one sample statistics, the summary of those 34 observations in our sample. How do I represent this 3.06 sitting next to it? It's a standard deviation. It's a standard deviation for my sample, so it is an S. What else do I put? S sub d, because it's on the differences. And then here, even next to that, is that nice standard error. SD over the square root of n, and n here is 34. So even the standard error is already computed. So it's not very hard to do part B. Give me a 95% confidence interval for that mean improvement, because that's kind of what I'm looking for, is an improvement, the mean difference in reasoning scores for the population. So can you start to work that out? What's the only thing you have to look up for me yet? A t-star value. And so try doing that out. You've got a t-table, maybe one you can pull out from your printed out note card, yellow card, or else go back, I don't remember the page number, and find it, or your neighbor has one. Try working out that confidence interval. And if you don't have a calculator, at least put in the numbers. And think about part C coming up, or even part D. Try out B, C, and D. You can look at D without being able to calculate the interval even. You're looking up a T star. What degrees of freedom would you like to use if you could? 33. And if it were being done by SPSS, it would use a T distribution with 33 degrees of freedom and find that value for you exactly. But if our table is all we have to use, then we're going to have to use what degrees of freedom? We fall in between 30 and 40. 30 is closer, but also the one we'll always use is to go back to the smaller. Because if you went to a larger value, you are assuming you have a little more data than you really do. And that might make your interval a little too wide. So let's use a little too narrow. So let's use the 30 degrees of freedom conservatively, and what is that multiplier? A little more than 2? 2.04. Some that are not used to the notation, I know I've made this statement before, but it says T star, SE, standard error, and then D bar. I get students on exam 2, because that's about means. They'll look up a T star perhaps correctly. Some put in 0.95 still. They'll put in the 0.52, and then they'll multiply by another 3.62, which is D bar. Because they think it's standard error times D bar, not the standard error of D bar, which is just 0.52. All right, what do we get for our margin of error? About 1.06, and an interval going from 2.5 points to almost 5, 4.68. We would estimate the mean improvement in reasoning for the population of preschool children, like our sample represents, to be anywhere from 2.5 points, 2.56 points, all the way up to possibly 4.68 points. And we give you that range of reasonable values with 95% confidence behind it. Now, part B asks you to think of that interval and, what value are you in particular looking to see if it's in that interval or not. It was that same null value that we mentioned earlier. What values of a particular interest to see whether it's in there or not? 0. Is 0 in our interval? No. So 0 is not a reasonable value for the true mean improvement. There does seem to be some effect of piano lessons on reasoning scores on average. We see that the value of 0 is not in the interval. So it's not one of those possible values for the population mean difference. What would 0 mean? 0 would mean no improvement on average. And we can refute that. It's not only that 0 is not in our interval, but the fact that what? Our interval is completely above 0. If it were completely below 0, both numbers being negative, that would tell us that piano lessons with our differences actually brought down the reasoning scores on average. And we hope that's not the case. It actually is completely above. So another comment might be here that the entire interval sits above 0. And let's even maybe write out a statement for interpreting the interval. What do we estimate? We estimate the population mean improvement in reasoning to be what? Between 2.56 and 4.68 points. We can put in there with 95% confidence, that's fine. In fact, that with 95% confidence is what is asked about in Part D, and that's your first clicker question of 2 today. There'll be one more coming up in a moment. Read Part D, and you're asked whether this is a correct interpretation or not. You see these results again and again. If you want to confer with your neighbor, you can. Read it all. Read it carefully. See if it passes for correct or not. All right, I'll give you 5, 4, 3, 2, and 1. One lone C. What do you think? Do you think the majority have it correct? They do. There is still something wrong here. It starts out beautifully if the study were repeated many times. We would expect 95% of those resulting confidence intervals, that's all good, to contain, do we expect 95% of the intervals to contain that sample mean difference, D bar? We expect 95% of the intervals to contain what we're trying to learn about here, that true but unknown population mean improvement or population mean difference. And here's where you have to make sure you do finish it out correctly with the right parameter that you're talking about in that problem. Now you have mu, mu d, proportion p, and the difference in two proportions that could go there. All right. This is, of course, interpreting the confidence level that was used in making the interval. The confidence level does not apply to the interval we just made in the sense of some probability or chance. It applies to the proportion of times that procedure gives you a good answer. All right, there's our confidence interval example. There's a little SPSS note on the next page. Quick look at that. I'll remind you that exam number 2 will likely be a page or maybe 2 pages longer. Why? Because there will be output. There'll be histograms to look at for checking conditions. There'll be output that have the summary measures and maybe the confidence interval already calculated for you. So when you're asked to provide the confidence interval, you don't have to compute it again and look up a t-star. You would actually just use the value right there. In this case, we did a one sample t procedure on the differences. Your pre-lab number 6 for next week will show you how you take data that actually has the 2 columns of data and you ask it to do the paired analysis and it'll calculate the differences for you. You can even tell it which way you want to do the differences and do the analysis. So you'll see that in your pre-lab. All right, and our last example to go through today is on the testing side. Same scenario. Page 143. You know how to write out those H naughts and HAs. Two pages left. We're turning to hypothesis testing for this parameter. H naught and HA always have the parameter in it. In this case, for all of our H naughts and HAs written here, the parameter is mu d. And what else do we know? H naught is the status quo, the prevailing viewpoint, or the statement that there is no effect, no difference on average. And so that's where the equal goes, and you usually are going to put it equal to what value? 0. Now, depending on how you define your differences, an improvement might be positive numbers. If someone defines the differences the opposite way you did, well, then improvement would be looking for negative numbers. They'll still get the same result at the end, the same p-value at the end, but how they define the differences make a change in what HA looks like. We might be looking for positive on average, or negative below 0, or just a change, that there is some effect, some change. And again, when they are the one-sided alternatives, if you decide to put the H naught to be the complement with the other direction in it, that's okay. But the equal needs to go there. So there's the typical set of possible hypotheses. Key here, if I give you the difference defined, then you're going to have to use that to know which direction of these two you might want to put. If I don't give you the differences defined and you have to calculate them, on your homework there's 5 pairs that you have to get the differences. You can decide how you want to calculate them, and then your HA might be different than my answer key for how I calculate them, but your t statistic would be positive instead of negative, and your p-value would be the same. All right, so our test statistic is going to be a t statistic. It is going to take our best guess, the sample mean difference, and compare it to what we said H naught, the mean should be, which is 0. So you can write the 0 there, or you don't have to. And then you divide by the standard error of that estimate. So here's how it's written out twice on your yellow card. It gives you the basic form with all 3 parts, and then it reminds you what that standard error looks like. And of course, you can drop the 0. If H naught's true, every test we have you do, we can say, if the null hypothesis is true, what's the model or distribution for your test statistic? It's asking you to say what model are you using to find the p-value. If it's a t statistic, it's going to be a t distribution. T distributions are what t statistics follow. And then, of course, which t curve are you talking about? Make sure you put in the degrees of freedom. It's still n-1 here because we're really looking at one sample of differences. The conditions are stated here again. Maybe, though, we want to highlight or circle. We better make sure we say it about the differences. You can have that checklist in your head, and I'll see this on an exam. What are the conditions? Random sample, normal. What's a random sample? Are the before measurements a random sample, or the afters, or the differences are a random sample? And what has a normal model? The normality is for the population of differences. All right, so those are our conditions to do our test. We look up a p-value as we have before. Let's try it out as our last example. About 5 more minutes, maybe. A knob turning experiment. We take 25 right-handed students at a device where there are 2 different knobs. One of them has threads so that you have to turn it to the right, and the other one has the threads the opposite way, so you'd have to turn it to make it move to the left. And turning it moves an indicator, and you have to move the indicator a certain distance, and that's the task. The question is whether or not, for right-handed students, are the right thread knobs easier to turn, on average, compared to the left thread knobs. The response will be how long it takes you to turn and make that arrow go a certain distance. So we're measuring time. Time is quantitative. I'll have the time for the person when they go up and do the right thread knob. How long did it take you? Okay, 20 seconds, whatever. And then they go up and do the left thread knob, and that takes them 22 seconds. So you have 2 times for each person. Why is this a pair design, and how should randomization be used? Well, it's a pair design because it's the classic one. Each person gets measured twice, a right thread time and a left thread time. I can imagine the data set. Here's your right thread time as one column of data, and here's your left thread time as your second column of data. And why would I want to compare that first number in each of those 2 columns? Because they came from the same student. 2 observations on the same person is why it's paired. It's a pair design because there are, if you want to think about it, 2 treatments on the same person. The treatment being which knob they have to turn. But randomization should still be used. We'll talk about later that randomization often is used to create independent samples. But here we still want randomization, even in our pair design. What should we do? What if we had every person go up and do the right thread knob first, and then they do the left thread knob? And maybe it does look like the right thread knobs are easier to turn on average, but it could be because you got to do that knob first. The order could be confounding here. If we let everyone do the first knob being the right thread knob. Maybe you decide and figure out, oh, it is kind of hard to turn. I've got to put a bit of muscle in. Maybe the muscle you exert, the strength you exert, can't be then applied to the next one. So that next one has a disadvantage every time. So we should randomize the order of which knob they do first. It is a pair design. We have 2 measurements on each subject. Two treatments, not necessarily before and after, but 2 measurements. And randomization should be used. We should randomize the order. The order of the treatments, per se, the knobs, which order they do first. Which knob is used first? How might you do randomization here? What could you do? If you don't have a fancy calculator with random numbers and so on, you could just flip a fair coin. If it's a head, they do the right thread knob first. If it's a tail, they do the left. It might be that my 25 people won't be evenly split. Maybe there'll be 15 that do the right thread and 10 that do the left, but it's still randomized. Or maybe I do have a random number or a hat with numbers 1 through 25 in it, right? Pick out the first 12 numbers randomly, and they get to do the right thread knob, and the other 13 do the left. Can't quite balance it perfectly, but that we could do. All right, so randomization would be important. Otherwise, order would be a confounding variable in this experiment. Here is the output. We need to state the hypotheses and perform the tests. So my last clicker question is for you to pick one of those 3 hypotheses that are the classic ones. Let you get started on that. See which one you're going to pick. And then we'll look at the output and just pull out the numbers to do the test in just a couple minutes. So you get to choose your hypotheses first. Question again is, are right thread knobs easier to turn on average? So are you looking for a direction? Are right threads easier? So you do want to look for a direction. Which one can we weed out right away? We're not just looking for a change between the two. It's got to be one of the directions. What do you think? Well, we're getting some B's and some C's. We've still got a few people with A's. And actually right now, I would grade both of these as possibly right. What do we have to define first to know which way we're going to go? The differences. Now, you might naturally go in one direction. If you did the right thread, then left, you might do that difference. But how you define the difference will determine which of those two is the correct one. Let's talk it through. So it could be either one. If we define the differences, let the differences be the right thread time minus the left thread time. Now, with that definition, can we pick the right one? All right, this is where you have to reason it through a little bit. You're talking about times. And if it's easier to turn, they should be able to turn it more quickly. So the time should be smaller. If the right threads are easier, if these are easier, then you can do it more quickly, which means the times should be smaller, less. If the left threads are harder, then it'll take me longer to do them. So my differences should be which way? A lower tail test. And if you peek at the output, do you see that in that last table it does say pairs, right thread minus left thread? So that is how SPSS calculated the differences too, to look ahead. I typically give you the definition just so you're all on the same page, so there is only one direction to go. But it is easier to still get the alternate direction mixed up if you don't think through that idea of time. Smaller time is better here. Lower tail test. Here's all of our output. We have a basic set of summary for each of the right thread and left thread times separately. Descriptively, were the right threads easier to turn? On average, was their average time to turn smaller? 104 versus 117. That difference is about 13 right there. So you have the summary of each set of data separately, but it's a paired analysis. And you know what? There will be clues. How do I know it's paired data? Oh, paired differences, paired data right there. Mu D is your hypotheses. All right, we have D bar. We have the standard deviation on those differences already calculated for us. We've got the standard error. What is N here? Is it 25 or 50? You have 25 measurements on the person and another 25 measurements. You have 50 measurements, but there's 25 differences. Degrees of freedom here, 24. The confidence interval is made for us, but we're doing the test. We're asked to report the test statistic. The t statistic is negative 2.914. I don't have to calculate it, although I could fairly quickly from my negative 13. Take negative 13 over the 4.6 standard error, and you've got your t statistic, negative 2.9. So yes, right threads were easier to turn on average in the sense that that sample mean difference was nearly 3 standard errors below 0. Then what else do we have at the very end that helps us complete our test for today? A thing called SIG two-tailed. T-tests by SPSS are always two-sided. They will always give you the two-tailed p-value. And you have to maybe take that and do the right thing. What's the right thing here? I've got a t-curve with 24 degrees of freedom. My observed test statistic was a negative 2.914. And I would like, for my p-value, the probability of seeing this type of test statistic value, negative 2.94, or something even smaller, less. And that which I just said is what you're asked for in one of your homework questions in homework 5, to interpret the p-value. We started with p-value definitions back in proportions, where we defined it. It's the probability under H not being true of getting your test statistic value or something more extreme, in this case less. I want that p-value right there. But that's not what's given. It's going to give me the two-sided one, so it gave me that one and this one over here. But I don't want that part. But they're the same. So 0.008 is what's in the two tails together. My p-value is what? 0.004. Probably 98% of the time, you do get to just divide that in half. There'll be a few times when You might have to do a 1 minus still as a final step. One of your bright yellow sheets in your workbook has a great write-up on finding the p-value from your t output. I'll reserve looking at this question and doing part D with you next time as a recap of paired, and then we'll move on.